Scientists just created a flash of light so brief that the universe barely had time to notice it happened. And I mean that literally. This pulse of X-ray light lasted less than 100 attoseconds. To put that in perspective, there are more attoseconds in a single second than there have been seconds since the Big Bang. Let that sink in for a moment. But here's what should really blow your mind. This isn't just about setting records. For the first time in human history, we now have a camera fast enough to film electrons as they dance around atoms. We're talking about watching the actual mechanics of reality unfold in real time. Think about every chemical reaction that's ever happened. Every breath you take, every thought firing through your brain, every photon of sunlight converted into energy by a plant. At the heart of all these processes are electrons, moving so fast that until now, they've been completely invisible to us. It's like trying to photograph a bullet with a camera from the 1800s. You'd never catch it. An attosecond is 1/quintillionth of a second. That's a decimal point followed by 17 zeros and then a 1. In the time it takes you to blink, about 300 million billion attoseconds have passed. Light itself, the fastest thing in the universe, can only travel about the width of 3 hydrogen atoms in 1 attosecond. Now, why does this matter? Because electrons are the architects of our world. They're the reason atoms stick together to form molecules. They're what makes chemistry possible. They're what allows electricity to flow through wires and thoughts to flow through neurons. And they operate on attosecond timescales. Until now, the best we could do was see the before and after. We'd start with molecule A, something would happen, and we'd end up with molecule B. But the actual process, the electron shuffling that made it happen, complete mystery. It was like trying to understand a magic trick by only seeing the setup and the reveal, but never the actual sleight of hand. The team that pulled this off, led by Uwe Bergmann at the University of Wisconsin-Madison and Thomas Linker at SLAC, didn't just incrementally improve existing technology. They discovered a completely new phenomenon that nobody expected. Here's what they did. They took the most powerful X-ray sources on Earth, machines called X-ray free electron lasers. These aren't your dentist's X-ray machines. We're talking about facilities that are literally miles long that accelerate electrons to 99.999999% the speed of light. The LINA coherent light source at Stanford and SACLA in Japan. Then they focused all that power down to a spot 100 nanometers wide. That's like taking all the sunlight that hits the entire Earth and concentrating it into an area the size of a pinhead. The power density is so extreme it's hard to even conceptualize. We're talking 10 to the 19th watts per square centimeter. When they fired this impossibly intense beam at a thin foil of copper, something remarkable happened. The copper atoms themselves became a laser. Not metaphorically. The atoms literally started lacing, producing their own coherent beam of X-rays. But here's where it gets weird. When they cranked up the intensity even more, they started seeing these mysterious hot spots in their data. Isolated points of incredibly intense light that shouldn't have been there. The computer simulations revealed what was happening. The X-ray beam was actually changing the optical properties of the copper as it passed through, causing it to self-focus into narrow channels like lightning branching through the sky. And then came the real breakthrough. At the highest intensities, they discovered the copper atoms were doing something called Rabi cycling. Instead of just absorbing and emitting light once, the atoms were frantically cycling between their ground and excited states, absorbing and re-emitting photons over and over again on sub-femtosecond timescales. This rapid cycling had an unexpected side effect. It was naturally compressing the messy, chaotic pulses from the X-ray laser into clean, ultra-short bursts. The simulations showed these bursts were lasting between 60 and 100 attoseconds, the shortest hard X-ray pulses ever created. Now let's talk about what we can actually do with this. Remember photosynthesis? That process that literally powers all life on Earth. The very first step, where a chlorophyll molecule captures a photon of sunlight and converts it to chemical energy, happens on attosecond timescales. We've never been able to see it happen. We know the before, we know the after, but the actual moment of energy capture has been invisible. With these new attosecond X-ray pulses, scientists will be able to film that process in real time. Watch the photon hit the chlorophyll molecule. See the electron get excited and begin its journey through the photosystem. Understand exactly how nature achieves its incredible efficiency at converting light to chemical energy. Or take catalysts. These materials make virtually every industrial process possible, from producing fertilizer to cleaning car exhaust. They work by manipulating electrons at metal surfaces, creating alternative pathways for chemical reactions. But nobody has ever actually seen how they do it. With attosecond X-rays, we'll be able to watch the electron exchange between catalyst and molecule as it happens. The implications go beyond chemistry. In quantum computing, the ability to observe and control electron states with attosecond precision could lead to entirely new types of qubits. In electronics, understanding electron transport at its natural timescale might enable computers that operate at petahertz speeds, millions of times faster than today's processors. There's even this mind-bending application called diffract before destroy imaging. The X-ray pulse is so brief that it can pass through a molecule and create an image before the molecule has time to explode from the radiation damage. It's like taking a photograph of a soap bubble with a blowtorch, but being so fast the image is captured before the heat arrives. But let's pump the brakes for a second and look at this critically. First off, the 100 attosecond duration wasn't directly measured. It was inferred from computer simulations that match the experimental data. The simulations are sophisticated and the match is excellent, but it's still indirect. However, and this is important, another research group led by Ichiro Inouye published complementary results at almost the same time. Using a different technique, they directly measured hard X-ray pulses between 100 and 400 attoseconds. So we have both theoretical prediction and experimental confirmation that attosecond hard X-rays are real. But there are serious challenges. The biggest one? These pulses aren't stable. The duration randomly fluctuates from shot to shot, anywhere from 100 to 400 attoseconds. If you're trying to make a molecular movie by taking snapshots at different time delays, having your shutter speed randomly change is a massive problem. The process is also incredibly inefficient. You need a miles-long particle accelerator consuming megawatts of power to produce a useful number of attosecond photons. And right now, this only works in very simple systems. Isolated atoms or molecules in a gas. The complex, messy environments where interesting chemistry actually happens, like inside living cells, might destroy the delicate quantum signals before they can be measured. There's another limitation nobody likes to talk about. These experiments require machines that cost billions of dollars and employ thousands of people. There are only a handful of facilities in the world capable of this work. This isn't becoming a tabletop technology anytime soon. But despite these limitations, what's been achieved is genuinely revolutionary. For the first time, we have a tool that can resolve both the where and the when of electrons with atomic spatial resolution and attosecond temporal resolution. We can finally see the ghosts in the machine. You know what's particularly fascinating? This breakthrough came from embracing chaos rather than fighting it. X-ray free electron lasers produce notoriously messy, spiky, unpredictable pulses. Scientists have spent decades trying to clean them up, but Bergman and Linker's team realized that under extreme conditions, that chaos could be harnessed. The random spikes and fluctuations, when pushed through the nonlinear physics of Rabi cycling, naturally organize themselves into clean attosecond bursts. It reminds me of how some of the most important discoveries happen, not by forcing nature to behave the way we want, but by understanding its inherent patterns and working with them. The copper atoms, subjected to unimaginable intensities, revealed a hidden organizing principle that nobody predicted. Speaking of unpredictable, the timing of this breakthrough is interesting. As global tensions rise and nations flex their technological capabilities, achievements like this remind us that the most powerful technologies often come from pure curiosity about how the universe works. The same physics that might one day revolutionize solar panels or quantum computers emerges from asking simple questions like, what happens if we hit copper really, really hard with X-rays? Here's something that should give you pause. Every process in your body, from the firing of neurons to the replication of DNA, involves electron transfers that happen on attosecond timescales. Until now, these processes have been too fast to observe directly. We've been like blind watchmakers, understanding the mechanism without ever seeing the gears turn. What happens when we can finally see those gears? When we can watch an electron tunnel through a barrier in a transistor, Or see the exact moment a drug molecule binds to its target protein? The answers might fundamentally change how we design everything from computer chips to cancer treatments. But perhaps the most profound implication is philosophical. We've always lived in a world where certain things happen too fast to see, where the gap between cause and effect contained mysteries that we could only guess at. That gap is now closing. The universe just got a little less mysterious and a lot more amazing. If you found this glimpse into the quantum world fascinating, stick around. Science keeps pushing boundaries we didn't even know existed.